Welcome back, everyone, to our last lecture of the day. It's my pleasure to introduce Krystal Guo.
Okay, thank you very much, Gabriel, and thank you to the organizers. I'm very happy to be here and to be back in Montreal. This mini course is supposedly about graph isomorphisms and matrix algebras. So the big picture is that the eigenvalues of graphs are graph invariants with respect to many choices of matrices. What I mean by that is that if you have two graphs that are isomorphic and you compute their eigenvalues with respect to the adjacency matrix or the Laplacian matrix, the eigenvalues be equal. And so it's very tempting to ask if it's a complete invariant. And that just means that if I have two graphs, I don't know if they're isomorphic. To answer the question of whether or not they're isomorphic, all I want to do is just compute the eigenvalues and compare the eigenvalue lists. So it'd be wonderful if that were true. And the answer is sort of yes and sort of no for various different classes of graphs. So basically what ends up happening is that, for example, for the case of strongly regular graphs, that the adjacency matrix does not distinguish strongly regular graphs of the same parameter set. Any two coparametric strongly regular graphs will also be cospectral. So then what you can do is you can associate with the graph like a more complicated matrix, a big matrix, but that will still be polynomial time to compute, and then ask for this bigger matrix whether or not those can distinguish the graphs. And for some cases, it's somehow like intuitively clear to people that this shouldn't really work, because that would mean that the classic strongly regular graphs, it would be in P, it would be polynomial time to distinguish those graphs. And they are an easier class of graphs to distinguish, or they are thought to be an easier class to distinguish than arbitrary graphs, but we do not yet know whether or not graph isomorphism is in P. So it seems like this shouldn't really work. But on the other hand, it becomes very difficult to show that these proposed algorithms for graph isomorphism in restricted classes with fancy matrices, it becomes very difficult to show that they don't work. So the idea is that we really want to, instead of discussing whether or not two matrices are cospectral, is to reduce the question to studying various cellular algebras surrounding graphs, some of which you have met and some of which you haven't met. Okay, so since everyone is starting with these, we can see if my LaTeX is working. So here's the list of basic topics. First, we will talk about distance regular graphs, although we won't, I've just looked at my list of examples, and it would appear that I'm only doing strongly regular graphs. It's actually supposed to check live as I type, but it seems to be a bit slow. And then we'll look at Bose-Misner algebra of graphs, but only as an example of a cellular algebra. And then once you have cellular algebras, there's a difference between strong and weak isomorphism. I think maybe a better name for these things is algebraic and combinatorial isomorphisms of matrix algebras, where what you want is some setting where if the graphs are actually isomorphic as graphs, you want the associated matrix algebras to be strong, to have a strong isomorphism. And if they are not isomorphic necessarily, but you want the matrices to not distinguish them, you want them to be weakly isomorphic. And then you can prove theorems about these types of things. So an important topic that comes up is this Weisfeiler-Lehmann algorithm, of which the easiest version is color refinement. It's where you color the vertices of the graph, or maybe groups of vertices of the graph, and then you do it iteratively. So at the next step, you color it with the colors of its neighbors in some way. And then this thing will converge, or eventually, hopefully quickly enough. And you can maybe determine if a graph is, if a pair of graphs are isomorphic. And we will talk about, some other algebras that occur later in the hierarchy of matrix algebras. And there are many open problems about how these algebras sit inside the associated hierarchy of matrix algebras or the Weisfeiler-Lehmann algorithm. Okay, but before we do that, since we kind of need a vocabulary to talk about, by which I mean we need to meet some graphs so we can discuss what does it mean to be an easier graph, easier pair of graphs to be differentiated, and what does it mean to be a harder pair. So basically now let us meet some graphs, and now things will become a bit more applied, or more introductory for a while, but this is a mini course, so I think it's allowed. All right, so the first, so we're going to see some examples of a strongly regular. Isn't that cool? It's like latexing it while I while I type. It latexes it by the letter. Okay, so the first example is the Paleograph, which I think many people are familiar with. So how do I specify a graph? I have to tell you some vertices and then some edges, right? So for the Paleograph, you need a number q. So let q. So q is a prime power, and it needs to be 1 mod 4. Okay. So now the vertices of the Paleograph, say, let's denote this P of Q. They are the elements of GF of Q, and they are adjacent when their difference is a square. So why is Q 1 mod 4? When Q is 1 mod 4, B minus A is a square, if and non-zero square, if and only if A minus B is a square. So it would be closed under inverses, so you will indeed get a graph instead of a digraph. In general, you can still get a digraph for odd Q. And this is an example also of a Cayley graph, where a Cayley graph is you have a group, and then which is the additive group of GF of Q in this case, and then you have two vertices are adjacent, or two elements of the group are adjacent if their difference is in some connection set. There's a very related pair of graphs. So Paleographs, they have some special properties. Do we remember the special properties of Paleograph? Paleographs are strongly regular. Yes, they are graphs, which are self-complementary. And how do we complete the sentence? So if you remove this arc transitivity and you replace it with vertex transitivity, then there's slightly more graphs. There's one more family, infinite family of graphs, and also one exceptional graph that you can read about in Natalie Mullen's thesis, master's thesis. Okay, so if we replace arc transitive with vertex transitive, there are also the Peiser graphs. So this is going to be so these graphs, they have the property of being the only graphs, well, up to this small exception that exists, which are vertex transitive and also self-complementary, strongly regular graphs of the same parameters when they happen to coexist. And so these are two constructions that are going to be very similar. So the Peiser graph, so the vertices of the Peiser graph are the elements of GF of Q, where Q is P to the, or P equal to 3 mod 4, a prime, and R even. They are adjacent if their difference is in the following set. So as a Cayley graph, I have to tell you what the things are. So it's just A to the J. It's all the powers that are 0 mod 4 of any generator, where J is equal to 0 mod 4, where A is a generator of the group of GF. So, so these are two graphs that are very similar, and they're so similar that the smallest example, which is also the biggest example that I am able to draw for you, they happen to coincide. So that's this guy right here. So here we have the elements of F9, which is constructed as a Galois field of F3 adjoining this element A, where A squared is plus 1 is 0. And then the vertices are just the elements of this field, but it's very small. So you can verify that everywhere I've drawn an edge, the difference of those things is okay. So that's a family of strongly regular graphs. What's another favorite family of strongly regular graphs that we could have a favorite? Good. You can read the slides from this far away. That makes it even better. Here's this classification of Neumeier that if you fix the least eigenvalue of the graph, then there are conference graphs, of which those two were an example. Latin square graphs and graphs from Steiner triple systems, and finitely many other sporadic examples. So we're hitting, all the basic, all the main things. So the Latin square graph, we're just going to do it by example. So the following is a Latin square graph, is a Latin square. It's this tiny little matrix here. So it's basically a Sudoku puzzle. It's an n by n array, such that in each row, I see the elements 1 through n exactly once. And in each column, also exactly once. So how do I get a graph from this? We get the graph by taking the vertices. The vertices of the Latin square graph are the locations in the Latin square. So they're going to be ij for I through ij from 1 to n are the location, and they're adjacent if they're in the same row, same column, or share the same entry. Same row, same column, or share the same entry. So the advantage of doing a board talk, but on your computer, is you can pre-LaTeX things. So, because I didn't want to make this table live, because that seems like that would be bad. So another way of recording the information in a Latin square is to put it in an orthogonal array. Okay, so how do I do this? Well, there's going to be 3 rows corresponding with row number, column, and the entry. And then each of these columns is going to be some location in the Latin square. So if, for example, I highlight this, I'm just putting those things in a random location. This column has been highlighted. Hopefully you can see that. So this column corresponds to the thing that is in row 2 and column 3, and its entry should be a 4. So row 2, column 3, it is a 4. So I did this correctly. Yay.
For this column.
Yeah, okay. Well, why don't you randomly select some other column? And we can also verify it works. Okay, but what exactly is the rule that I need here? What's the rule for the Latin square to check that I've filled it in correctly if I took away the original Latin square? It has to do with pairs of columns and how many times the ordered pair occurs.
Oh, it's orthogonal. I didn't know what your question was.
Yes, yeah, as an orthogonal array. Yeah, so if you look at, that doesn't highlight. But if you look at the first 2 rows, or the first and the third row, you look at these pairs, every ordered pair of elements in n, they should appear exactly once. But now you know that that's the rule. You can also do this with more than 3 rows. So you can have orthogonal arrays with different values of 3, and the rule remains the same. In any case, for the orthogonal array, it's easier, maybe even easier to see when they're adjacent, because now the vertices are just the columns of this orthogonal array, and they're adjacent if they share some entry in any of the rows. So in this setting, the vertices are columns, or rows if you wanted to have it be really skinny, but we wanted to put it on a screen. In this setting, the vertices are columns, and they are adjacent when they share an entry, when they agree on some row. So that's 2 classes of things that give you strongly regular graphs, or our goal was distance regular graphs in this case. Yeah.
Stupid question is so obvious. Why is that orthogonal?
Definition of orthogonal array.
No, like one.
It's orthogonal in like a combinatorial way. So I think the reason it's called orthogonal is if you look at all the things that have 1 here, you should see like 1, 2, 3, 4 in the other rows. So that's the way in which it is orthogonal, not that 2 things multiply to 0. Yeah, and then if you look at all the places where this column thing has 1, if you look at the other 2 rows, you should see the symbols 1 through 4, like permuted somehow. Yes, that would work. All right, so that's 2 families of strongly regular graphs. And I'm only going to do 1 more family. And if you think this was hand wavy, it's going to be even worse, because now we're going to do generalized quadrangles, which are maybe the main thing. Oh yeah, so sorry, you get a strongly regular graph, but now maybe not for this order because it's super small, but for other orders, you can imagine that you can have different inequivalent Latin squares or inequivalent orthogonal arrays, and they should give you non-isomorphic graphs, but they will have the same parameters as a strongly regular graph. So a strongly regular graph has these 4 parameters: the number of vertices, the degree of each vertex, the number of common neighbors for a pair of adjacent vertices, and the number of common neighbors for a pair of non-adjacent vertices. So for these things, it will be n squared vertices, and every vertex will have, 3 times k, 3 times n minus 1 neighbors, and so on. So, but it does not depend on the specific orthogonal array. So this is one way to generate many strongly regular graphs who cannot be distinguished by the eigenvalues of their adjacency matrix, which is why people want to associate other matrices which do distinguish them. Okay, so the third construction for strongly regular graphs, for which there might be many, or at least more than one, that might confuse an algorithm trying to distinguish strongly regular graphs, is a generalized quadrangle. So very similar to standard triple system. So then I'll have hit, all the greatest hits of strongly regular graphs. But it's a point line incidence structure. So a point line incidence structure has some things called points, some things called lines, and then an incidence relation between the points and lines. So a point line incidence structure has points, lines, and an incidence relation. Tells you which points are incident to which lines. Some examples that you might be more familiar with are projected planes, affine planes, etc. Okay, so let us just draw the definition of a generalized quadrangle. The reason I had to share the entire screen. So a generalized quadrangle, did it share? Okay. Denoted GQST is a thing that takes as input. So it's a generalized quadrangle. It's a thing that takes as input 2 numbers, S and T, and it's an incidence structure. So I have to tell you some rules about some points and some lines. Okay, so Bill had a cute thing for doing this, so maybe he'll supply us with it. So the first rule of generalized quadrangle is that if I have a point, I can look at how many lines go through this point. Oh God, how do I make it go? So there are some number of lines that are incident to my point. And when I draw them in a geometric sense, I'm just going to draw the point and then the lines will intersect it, like we were to do in geometry. And the rule is that there are t+1 such lines. So then if I look at some line of my generalized quadrangle, well, it's going to be incident to some points. How many points, which I'm drawing as points that lie on here, and how many points is it incident to? It must be incident to s+1 points. So Bill has some mnemonic that helps you remember it, except it doesn't work that well. So it's like t+1 points, t+1 lines go through a point, and s+1 points sit on a line. But there are clearly other words that start with S and T that could totally mess this up. Okay, so yeah, the points, they all have the same size. They're incident to the number of things. The lines, they all incident to the same number of points, S+1. Okay, and then the important rule is the following, that suppose you have a point here, and then some line that it is not incident to, down here, then there is a unique other point that is on this line, such that there exists a line through your original point. There is a line incident to these 2 points. So this is sort of the picture. What that means is that there does not exist some other point over here, which we can make red to indicate this is a no-no, such that it's also collinear with the original point. Let's make that clear. No. Okay, wow, it showed up in red. Okay, so this is why this is called a quadrangle, because if we draw the drawing like this, it just means that when I draw the drawing of which things are incident with which points, I cannot draw this triangle. The smallest thing that could exist is a quadrangle. So this is called the generalized quadrangle for this reason. Okay, so that's the definition of generalized quadrangle. Amazing, definition done. Okay, so from a generalized quadrangle, we can extract many graphs, but the one that we care about the most is the point graph of a generalized quadrangle. So the point graph, oh, it woke up, okay, of a generalized quadrangle, a GQ, has vertices, has points they are adjacent if there exists a line that they're both incident to, or as we say in geometry, if they're collinear. And 2 vertices points are adjacent, are collinear. There exists a line incident to both points. Simple enough. There are other choices for graphs that we could have constructed from our GQ. We could make the vertices lines. We could take both the points and the lines to be vertices and have an edge when they're incident, and that would give us the incidence graph, some of which are also distance regular graphs, but we're just going to use the point graph. So the parameters of the point graph, the parameters are, okay, so the number of vertices, it will be s+1 times st plus 1. The degree is s times t plus 1. And then number of common neighbors of an adjacent pair is s minus 1. And the other number is t plus 1. So now you may notice that this s and t had better satisfy some conditions, because once we start counting things, we want certain combinatorial identities to hold. There are only a few known cases for S and T where generalized quadrangles are known to exist. So there are only a few families, by which I mean, values of S and T where GQST is known to exist. They are the following. They are so few that I'm going to list them, or maybe try to list them. Yeah. Okay. So 1Q is possible. This will just give you a grid, toroidal grid. That also will be a generalized quadrangle. It will be a point graph of the generalized quadrangle. Okay. And then Q minus 1, Q plus 1. Okay, yeah. It's completely about, sorry, yes, the incidence graph will be the grid. You're right. Okay, so there's Q minus 1, Q plus 1, QQ, and QQ squared, and Q squared. Where Q, as usual, is a prime power, the duals. So if I switch the roles of the points and lines, I still get a generalized quadrangle called the dual, and it will satisfy all the requirements as before by duality. So I'm only going to write the ones where that first coordinate is smaller, where s is smaller than t. So first open problem is that there are some parameters which have not been ruled out, and yet no graphs exist. So these are all the known parameters where there are infinite families, but there could be more that we have not yet found. So here's an open problem. The following values for S and T, they're feasible, they're infinitely feasible for all values of Q, but no graphs are known. So there are only two families, and of course the duals. So it's a Q and Q squared minus Q, and Q squared minus Q minus 1. Clearly the open problem is to find some, and or to show that they don't exist. But maybe you want a more concrete example. So the smallest known case is GQ411 and GQ412. So in particular, does there exist Q411 or GQ12? Those are the smallest cases.
So you keep saying like series and series and series. So they're like some sporadic weirdos that are known to exist or not known to exist.
There are no sporadic GQs.
Okay.
So these are the only families, but some of them don't exist for small order, I think. The Q has to reach a certain number, like 2 or something. And also you might, okay, so these are the only feasible ones. There are no sporadic GQs. No sporadic GQs. Okay, but these numbers will be kind of big. The number of vertices involved, there will be like hundreds in the smallest cases with these small S and T. So it's hard to search for them computationally. And all the small ones that you have, because they're so small, it's kind of easy for them to fall into one of these cases whenever they have been constructed. So this is the issue, that you say, okay, GQ36 exists, but maybe it's one of these things or doesn't exist. So this is the first infinite family where there's nothing number theoretical that prevents this from existing, and yet we have no construction for any Q. And the smallest example being 411 and 412. I think the smaller ones, you can know that there are proofs that sporadic examples don't exist for small Q. So for example, for the smaller version, either it coincides with this family here, one of these, or it doesn't exist. So that is known. Okay. So in the construction, they're all prime powers because they're all constructed using other geometries and over finite fields. So you need the Q to exist. Also not ruled out. That's right. So the non-prime power, because this is feasible, it will also be feasible when Q is not a prime, doesn't affect those conditions. And yet we also know no example. Okay. So maybe another question is that from this, there does exist one GQ416, and it's still open. whether or not there exists a second one. It is also unknown whether or not there exists two non-isomorphic GQ 416. I believe the smaller order, GQ 4 and GQ 39, those are known to be unique. There is only one, belongs to whatever family it belongs to. And there's only one up to isomorphism. But GQ 416, there is a construction that exists. 4 is after all prime power, but we don't know if it's the only one. And why would we care about such a thing? Well, every time that you get a GQ, you can see you get a strongly regular graph of these parameters. This only depends on S and T. So this is a good way to construct two cospectral graphs. And there are two cospectral graphs that are very, very similar. The point, we know from the definition that every point sits on T+1 lines. No, okay, there are T+1 lines through each point. Oh my God. Yeah, okay. This is how it goes wrong. Okay. But there are S+1 points on each line. So that means the maximum clique of this graph is going to be S+1. And indeed, every vertex will sit on T+1 maximum cliques. So this is a special condition. This doesn't hold for other GQs. You can other strongly regular graphs. So you can have strongly regular graphs that are cospectral with these strongly regular graphs, and they will not have this property about the number of max cliques that a vertex lives on. And that can exist as well. But this is a good way to construct two graphs that are very, very, very similar. They have like some structural similarity with these cliques, and also they have the same eigenvalues. And can we differentiate them? Can we not differentiate them? I don't know. Now let's discuss that. Distinguishing. So now we want to distinguish strongly regular graphs. Now there is one school of thought when it comes to distinguishing graphs of spectra, is that you have your adjacency matrix and you compute the eigenvalues with respect to the adjacency matrix. If that graph is the only graph to have those eigenvalues, then you say that the graph is determined by spectrum. If it doesn't, if it has a cospectral mate, a little friend that has the same eigenvalues, which, for example, the Peterson graph doesn't have, then you just admit defeat and, concede. But, we can do more. So suppose you have graphs that have a cospectral mate. What you can do is you can just define some other matrix and look at the eigenvalues with respect to this other matrix. And we're going to talk about such algorithms later. So one can associate with a graph many matrices. And so there have been many proposed algorithms for graph isomorphism in the class of strongly regular graphs, which use various different matrices. So we'll see several of these matrices in the next few days. So we will look at several of these matrices over the next few days. So I mean, there is some cutoff, right? You want to associate it with some matrix that is easy to compute, given your strongly regular graphs, whose eigenvalues are also easy to compute. So if you associate with it a matrix that is exponential in the number of vertices, then maybe that does distinguish the graph, but it won't give you a polynomial time algorithm because you would still need to compute the eigenvalues of that huge matrix. So you don't want that. And also, clearly there is a way to cheat because you can take the graph 6 string of the graph and you can stick it in like a 1-by-1 matrix. And now that thing has one eigenvalue, which clearly will determine the graphs. The canonically ordered graph 6 string is such that if you have two graphs, you canonically label them, take the graph 6 strings. Those things will be equal if and only if the graphs were isomorphic. So you can clearly cheat this by allowing you like infinite computational power. The graph 6 string.
Just look like that code. You deeply identify the graph as a 1-by-1 matrix. That's an eigenvalue calculation.
So for example, you can take the adjacency matrix of the graph and you look at the upper diagonal, the upper triangular part. So you can concatenate all those rows to get some really long number in binary. So you can stick that number in whatever you want into a matrix. That will sort of determine the graph. Now it can be up to isomorphism because you can look at the canonical graph 6 string is you look at all the possible adjacency matrices of your graph and you take the one that comes lexicographically first. So now this will determine it. But obviously this takes a long time to compute. So we don't want that. You want something that is still like a reasonable amount of time to compute, polynomial, and that maybe determines the, you don't know, it depends on like, you don't, sorry?
It could be that that's swing.
Yeah, you're right, okay. Yeah, so, but there is no known algorithm such that for any input graph, it can output in polynomial time, the string that should be canonical for the graph. So that, but anyway, there's stupid things that could happen if you allow too much computational power. So what we're thinking of are graphs that, sorry, are matrices that are not very big. So the examples include, and I'm gonna briefly list them, symmetric squares. So symmetric squares, here you take, so a lot of the ideas for these other matrices you can associate with the graphs is in the adjacency matrix, it's going to be vertices by vertices, and you put a 1 when they're adjacent. So what you can do is you can index your matrix with bigger objects. So in the symmetric square, you take pairs of vertices. So there will be like the number of vertices squared, number of, or maybe choose 2, number of rows and number of columns. And now between 2 pairs of vertices, I put a 1 if their symmetric difference is an edge. That's how you construct the symmetric square. So this works sort of well, but it doesn't work for strongly regular graphs. So it will not distinguish strongly regular graphs. So of course, the next suggestion that people came up with is symmetric powers. So here, the vertices, sorry, the labels of your matrices are k tuples of vertices. So it's a matrix indexed by k tuples of vertices with a 1 in the corresponding position if 2 k tuples have a symmetric difference, which is an edge as their symmetric difference. So the symmetric square, that's for k equals 2. So this thing is proposed to be a graph invariant for strongly regular graphs, and there's no known pair of counterexamples. And also various quantum walk inspired algorithms. Okay, so for these, the matrices come from various transition matrices of different types of quantum walks, but there's nothing quantum about them. So what will happen in the end is you have a completely classical matrix of which you need to find the eigenvalues to determine whether or not graphs are isomorphic. So that's the proposed algorithm. So maybe the first one that we will see symmetric powers later on, and then we'll also see another quantum inspired one. But I'll just give you one example now in some amount of detail. So discrete time quantum walk. Yes. I think so. Yeah. No, k subsets. They should be k subsets. I think it doesn't make a difference because then you just have many copies of the same k tuple. The incidence relation or the adjacency relation is only about their symmetric difference, which only cares about which set it is. So it would be like taking the Kronecker product with some all once matrix. Oh, okay. No, it's not multi-set. It's just yeah. Okay. But that also you can deal with because then you can take the k subsets and then k minus 1 subsets and so on. So in the matrix algebra setting, you're just taking the union of all of the littler matrix algebras as well, projected into the bigger one. So somehow, yeah. So there is some redundancies that can be added, and also you can reduce this. I mean, what you don't want is to show that symmetric powers do not distinguish strongly regular graphs, and then someone comes and says, okay, now we take multi-sets. And that would be a little bit annoying. So, but you can I think you can, these things will be in the bigger algebra, and you can also eliminate such things occurring by some product, hopefully. Okay, so maybe I give you a specific example of such a matrix that is, that determines some strongly regular graphs. So the transition matrix, the discrete time quantum walk, which there will be talks about next week, right? Yeah, so the discrete time quantum walk It's just a quantum process on a graph. I don't know why I'm writing this. This is a sentence that has no syntactic meaning. Okay, so but what does it do? The point is that it has a transition matrix, which is going to be some matrix with combinatorial information. The important thing for combinatorialists is that it has a transition matrix, which has combinatorial information. So we take a graph and replace every edge with two oppositely directed edges. So you make it directed, a diagonal, and replace every edge with two oppositely. So now you can define two incidence matrices of the graph. So every edge, there is a head and a tail. Okay, I don't see any chalk. Oh, okay. Yeah, to draw this super useful diagram, is this a defective one? Okay, so this is what an edge looks like, and this one is the head, and this one is the tail. Not, if it should be the other way around, it will still work. Oh, wow. So now we can define an incidence matrix, the head incidence matrix. Okay, it is a matrix indexed by vertices and directed edges. So it's going to be V times twice E, V times 2E, where it's an incidence matrix. It has zeros and ones. I just have to tell you what it is, but it's just that the two entries, it's going to be 1 if that vertex is the head of the edge. It's a matrix, blah, blah, blah. It's a matrix whose name is D sub H. Very creative. D sub H, where D sub H, if I look at the thing that's indexed by the vertex U and the edge E, this is equal to 1 if U is the head of E. So similarly, we can define the tails incidence matrix. We have the tails incidence matrix. So this is just the, so it's also indexed by vertices versus edges, and you still have the 1 when that vertex is the tail of that edge. Okay, so then we also need one more thing. So let P be the 2V by 2V, no, 2E by 2E permutation matrix that takes every arc to the opposite one. There are some arcs, and then you just want to pair them off as those that are UV and those that are VU. So it's a permutation matrix that takes every arc to the oppositely oriented arc, which takes each arc or directed edge to the oppositely oriented. Okay, so what that will mean is that dt. So this is V by 2E. If I multiply by P on this side, I will get D because I'm just swapping it out. If something was incident in here before, that means that that vertex is the head of the tail. Once I apply the permutation, the vertex is now the tail of that same edge. So I will get the DT in this way. So you can take one of these with the P matrix, or you can take both of them. And what may not be immediately obvious is if you take DT times DH, so that's the right size. It will be vertices by edges, edges by vertices. Okay, and it's V by V. This will be equal to the adjacency matrix. At least it's the right size to be equal to the adjacency matrix. Good. Okay, but it will actually work out these extra rows because now you have two columns corresponding to each edge. It will still work out, and the diagonal will be fine. The diagonal will be 0. Okay, and then obviously it would also be okay if I put DH, DT, and there are some other ones. So if you multiply two of them in this way, DH with DH transpose, you should get an identity. DT with DT transpose, also the identity. So there are some very simple ways in which this is related. So the transition matrix, okay, almost of the discrete time quantum walk, okay, discrete time quantum walk is the following. So it's U is equal to for a regular graph, sorry. But certainly we're only working with like association schemes. This is gonna be fine. Which way does it go? D, oh my God, DT transpose, DH minus the P of a K regular. So it will just be this matrix. This is the transition matrix. What it means is that at time T, if I have the state vector, at time T, I just take the tth power of this U matrix, and I would get the state after time t. We are not going to use that in a quantum sense. All we're going to do is use this to make some other graph invariant. So there's a paper by Ems, Severini, Wilson, and Hancock in 2006, which proposes to use the following matrix, S, to use the following to distinguish graphs, or maybe strongly regular graphs, by their spectra. So they want to take the positive support of U cubed. So they want to take S is obtained from U to the third power by replacing all the positive entries with 1 and all other entries with 0, with 1 and all other entries with 0. So their proposed algorithm is you can compute this thing because you can compute these incidence matrices. That's not going to be too bad. And you can take the cube and then you can go through and replace entries as needed. And then the proposed algorithm is you have two graphs, you do this process, you take the spectra of the two S's that you get, and they should only be equal if those graphs are isomorphic for the class of strongly regular graphs. Okay, so that's their thing. Maybe we think that shouldn't be true. But the thing is, it does work very, very well. So this does distinguish many pairs of strongly regular graphs. So for example, we've already discussed that the Paley and Peiser graphs are cospectral with respect to the adjacency matrix. The smaller ones that you can compute, they are not cospectral with respect to this matrix. Okay, so there exists non-isomorphic Paley and Peiser graphs with parameters, how big it has to be? 49, 20, 11, 12, which are distinguished by this process, For odd Q, GQ, is not isomorphic to its dual, and they're also distinguished by this process. GQ, QQ is not isomorphic to its dual. They are distinguished by this for Q, for small q, mostly Q equals 3 and 5 because they become really, really, really big. These are some classes of graphs. And of course, when they proposed their algorithm, they computed all the ones on Ted Spence's website of strongly regular graphs that they were able to compute. And this thing does distinguish them. So for example, there are approximately, 30,000 isomorphism classes of strongly regular graphs on 36 vertices that come from Latin squares. And they're all distinguished by this abnormal matrix here. Okay, so, right. So, but this doesn't work. This algorithm doesn't always work because we did manage to find a counterexample with Gotzel and Tor-Michelbust. We did find a pair that this does not distinguish a specific pair of GQs. We did find that this does not a specific pair. So in particular, there exists two GQs, GQ 5, 25, 5, 525, which is smaller, this one, and which are not distinguished. This was a deeply painful thing to compute because that matrix is 98,280 by 98,280 is dense, and it's a 0-1 matrix and it's not symmetric. I think part of our code, we needed to just square the matrix, and this took just 1 week for the computer to simply square this matrix. So even if one entry of this thing takes 1 byte, it would take a terabyte to store this thing. So this was really beyond computation. So what is the solution? I mean, we really don't want them to come back and say, okay, now we take you to the 4th, and now we take the positive support of that thing. So the thing to do, clearly, is to try to find the correct matrix algebra that should be associated with this matrix, and to show that the matrix algebras are cospectral themselves, or weakly isomorphic in our language. So this is sort of the motivation for, the pain in this computation is the motivation for why we would like to move to the matrix algebra setting. Right, so I think I'm out of time. So yeah, in the next class, or in the next, part of the mini course, we're going to look at where this lives. And I wanted to leave you with one more thing. Okay, no, it's going to take me too long. But basically, even this s plus of u cubed with the positive entries replaced by 1, you can write this as a very long equation in dt, dh, the adjacency matrix, with usual multiplication and with one short multiplication. So from this, you can sort of see that maybe it's easy to define a large coherent algebra. And you can see that it will live in some product of the Terwilliger algebra from the equation that I don't have time to write.
Thank you very much, Krystal. Do we have any questions? Yes, Bill has a question.
Go, Bill.
I don't know which strongly regular graphs are determined by their spectrum. There's a trivial example where the non-regular graph that has the same eigenvalues as the strongly regular graph. But in general, if I give you the spectrum of the strongly regular graph, is it guaranteed that there's no non-regular graph with the same eigenvalues?
The characterization is only for regular graphs. If you're regular and you have 3 eigenvalues, then you must be strongly regular. But I think there are other cases when you can make disjoint graphs. No.
Like a complete bipartite graph, 2 by 25 has 2 by 32 has the same eigenvalues as, but for non-bipartite strongly regular graphs, no imposters.
There are some imposters, aren't there? In Edwin's
Non-regular
thesis?
graphs with the same exact spectrum as a known strongly regular graph.
I'm not sure, Bill, but there are some similar things. Edwin's thesis has the 4 eigenvalue graphs and imposters. I think there are some that are.
So this last process you mentioned with S not distinguishing this GQ 525.
Yeah.
Do you, in the distinguishing process, do you just ask if the matrix itself distinguishes, or is it?
No, we compute the eigenvalues.
Okay.
They have the same eigenvalues with respect to that crazy matrix.
I see. Okay.
So there are 2 matrices that are 98,000 by 98,000, and then we computed their eigenvalues. So it took like 4 weeks to square the thing.
I see.
Okay, 1 week each to square them. So we couldn't find the eigenvalues just completely, right? Like what we could do is generate loft spaces at random to try to guess the minimal polynomial of this. And after a certain number of random trials, you can be sure about the minimal polynomial. And it had no repeated roots. So now you know the thing's diagonalizable. So now you can solve for the multiplicities. And then because we generated many Krylov spaces using randomness, you can have lower bounds on what the multiplicities of the eigenvalues are. And then we computed the square of this terrible thing, just classically. And from that, you can find a trace of this thing to the cube and the trace to the 4th. So now you have a whole bunch of equations about what those multiplicities have to be, and we solve them. And there is a unique solution in both cases, the same unique solution. So that's sort of, I mean, this is at a point where their algorithm is very difficult to implement with current computational power.
Okay, and another question is, why are you focusing on strongly regular graphs? Are these particularly hard?
Actually, they're not. I think they're particularly easy to distinguish. So right now, the best algorithm for graph isomorphism is Babai's quasi-polynomial time algorithm. But before then, there was a general algorithm for graphs, but then there were many subclasses. So for example, it is polynomial time for bounded multiplicity eigenvalues, for simple eigenvalues. And also, there was an algorithm also by Spielmann for strongly regular graphs, and it was faster, like for a very long time. So it was sort of felt that this is a classic graphs for which it is graph isomorphism may be an easier problem than the class of arbitrary graphs. And that's why so many of these algorithms have targeted this class.
First case, but like you said,
Yeah.
Spielmann is a different algorithm.
No, but Spielmann, it knows that both graphs you inputted are strongly regular, whereas Babai, you need to distinguish it from the possible all other ones. And he uses color refinement in an earlier stage, and that definitely doesn't distinguish regular graphs. So if you would have, yeah, it would be in like already a hard case in his partitioning from this.
Questions for Krystal? Let's appreciate him.